Okay, I'm very happy to present Dr. Rafael Lang from Purdue Physics Department. He's been so gracious as to come down and give us a demonstration of what dark matter is. In fact, we don't know anything at all about it, so now we're ready to go home. So, Dr. Lang?
Thank you very much. Okay, so pause, right? I mean, so far I did everything wrong I could do, right? I came late, it didn't work. Now the USB stick I have my talk on doesn't seem to work. So okay, so we'll just try to patch that. Here's the main and foremost thing. Thank you very much for the invitation. First of all, is what I want to say. It's a great pleasure to being here. So far. We'll see what happens. Okay, so I would like to keep this evening a bit informal. Okay, I mean, I guess you are here because you want to know a little bit about dark matter. I guess you have heard a little bit about it. You know, are dark matter, is that something about black holes? No, not at all. Has nothing to do with it. I want to try to get a little bit about it across about what we know, but also about what we don't know. Now, I have on this USB stick, which seriously doesn't seem to work. Oh wow. I have something like, I don't know, 150 slides, and there's no way I'm going to show all of them. I don't want to, right? What I want to do is I want to tell you guys what you want to know. And what I have is I have some teaser slides to you know, get you started and show some things that I think are important. But really, if you have a question that's on your mind, please do ask and ask any time. The main thing is also, yes, there's one, and I'll keep that in a second. And the main thing you have to realize in a crowd, even just a tenth of if there's 2-3 people in the room and one person has a question, you are not the only one having that question. The other person sitting next to you has the exact same question. So please ask any time. And there's the first question. Yippee!
Would you define matter?
Yes. Okay. So dark matter, what is that? And dark energy, what is that? And dark matter is whenever we look in the universe, and I found it. That works? Yeah, fantastic. We take the PowerPoint. Whenever we look in the universe, no matter at which scale, be it very locally, the smallest thing where we see that is our own galaxy, the Milky Way, or be it the whole universe as like the whole thing, right? The cosmic microwave background. No matter at which time we look, do we look very close to the Big Bang, just minutes after the Big Bang, or do we look today, right, in our Milky Way? All of the universe points us to the same piece of, thank you very much, please applause. It all points us to the same direction, and that is, there is stuff, matter, I'll define it a bit better perhaps in a second, missing on all those scales, and we can explain, you know, more than a dozen of independent observations that we have. And again, I'll just show you a few of them, and you can ask me a few more. This one? That's not the good. The guy back there, he'll fall asleep. I mean, he's already. We can explain all that if we just make one assumption. There is matter, you know it, like a table, like a chair, or more precisely, some kind of particles, like protons, neutrons, electrons, you've heard of those, out there in the universe that we haven't detected yet. There's a lot of them. There's about 10 times more of that kind of matter than all the matter that we know together. If we make only that one assumption, we can explain this dozen of different observations just with one go. That is what dark matter is. Dark matter, in this definition, is the stuff that explains all those explanations at the same time, observations at the same time. Okay, so myself, what am I doing? I spent my time since last summer. I joined at Purdue, and I'm actually I'm trying to figure out what this dark matter is. And I have a few slides about how we try to build detectors that, if we are happy, can catch this dark matter. We can learn something about it. So far, we haven't succeeded. Spoiler alert! I spoiled it. So. What I want to get across is, well, what is this dark matter? The first thing that I want to say, the questions to be answered. The first question is hunting dark matter like hunting Bigfoot. You know, you search for something and in the end it's maybe not even there. And there the answer is a clear no, because we know much more than this blurry picture now. By now, this is this advertisement of Sony. I found it cool. If you look very close, you see a zipper line here. We know a lot more about dark matter these days, that it's fair to say that it is very reasonable that dark matter is out there. Having said that, do we have any clue about what this dark matter really is? I mean, could it be a small little man like this one, like this guy, right? And the answer to that is, well, not really, right? We know what it isn't. We know that it's not stuff like that made out of polymeric clay. We do know quite a bit about where it is, where in the universe. So that's where the pretty pictures come in. It's always great as an astrophysicist. You can show pretty pictures. So that's where those come in, right? We can look at the universe and see where this dark matter is. So that's what we know. We know a few things what it isn't, and we know where it is. But that doesn't mean that we know what it is. Frank answers, at this stage, we have basically no clue what it is, unless you count knowing what it isn't, being having a clue about what it is. The question then will be, well, can we test our ideas? Of course, there's millions of ideas, right? I mean, there's all the scientists out there which have nothing better to do than to cook up ideas what this dark matter could be made out of. And is there any hope that we could test those ideas? And the answer to that, and that's what I want to get across tonight, hopefully, is a clear yes. Yes, even if we don't know yet what it is, we have a set of ideas and we can try and go fishing for those ideas. Even if you have never seen a fish in your life, you know, you can go out in an ocean, throw out a net and see what you get. And if you're lucky, you get a fish. If your net is too coarse, right, then you don't get a fish, bad luck. But even without knowing what a fish is, you can go fishing. And then again, I want to stress that most important to me is your questions, the questions that you asked. I'm happy to answer them anytime you have them. So please feel free to interrupt me. What is dark matter? I want to start locally and go to bigger and bigger scales to give you a few ideas why today everybody's talking about dark matter. Where does it come from? So there's a picture of the whole night sky, and particularly the Milky Way. You see this Milky Band, this is the center of the Milky Way. You see there's a little bit of a bulge there, right? It's a bit thicker there, there's more stuff there. The Milky Way, well, we all know that is a disk, right? So there's the stars and the nebula, basically everything you can see with the naked eye, except for the Andromeda Galaxy, all belongs to our Milky Way. So all that stuff is going around in circles. Now you know that from your merry-go-round, right? If you go around in circles, you have to hold on, because if you don't do that, you fall off, and that hurts, so you better hold on. So here's my question. Hey, I'm asking question 2, so how mean is that? So here's my question to you, it's just to make sure that you don't fall asleep. So here's my question to you. In the Milky Way, right? So we have all those stars going round and round. They will try centrifugal, we can argue about that, centripetal force. The centripetal force will try to blow the Milky Way up, right? It'll try to rip it apart. But so there needs to be some kind of glue that keeps it together. Same thing, if you're on a merry-go-round and you go round, if you don't want to fall off, you need to hold on. You need to have a force that keeps you together. What's the force in the Milky Way that keeps the Milky Way together? Gravity, right? Oh, that was fantastic. That was easy. Okay, so now what we can do is we can do an exercise, and I try to leave out equations. Is that appreciated or not? Because if you want some equations, I have them also. Maybe I forgot to take some of the equations out, because some of the believe it or not, actually some of the slides I show you tonight are the same slides that I show to my colleagues if I go to another university giving a seminar or colloquium talk. So, you know, it's not all about equations, it's also about pretty pictures. Which is good, right? It makes more fun. Okay, so you can work it out, right? If you know how fast you go, you know how big the centripetal force is. I mean, as a matter of fact, it's just mv squared over r. You do that in the 11th grade at high school, probably. We can... okay, whatever. Take my word for it, you can easily work it out, right? And if you want to know, then you ask the question, you bore the rest of the audience, and we'll work it out. I can look at the Milky Way, and I can look at the stars, I can see how fast they go around. So that means I can work out easily how fast is the centripetal force that tries to blow the Milky Way apart. At the same time, I know the Milky Way doesn't blow apart, right? It's still there, we're still here. So there has to be enough gravity to balance that force. Now where does the gravity come from? Well, again, I can just look at the Milky Way and say, okay, now I know all the mass that is there. So I know the mass, you know, Newton's gravity, g(m)m over r squared, if you like equations. If not, just forget what I just said. Newton's gravity, you can plug that in, and you can work out how strong is the gravity. Now here's the bummer. If you do that, what you find is that the gravity that is caused by all the mass that we can see, all the matter that we can see, is much too weak to balance the centripetal force. Bummer, huh? With much too weak, I mean much too weak, a factor 10, right? It's not that, you know, you have like in a few decimal places some small effect where you say, oh, you know, maybe there's some planets that we didn't account for or something. No. You can throw in as many planets as you want. No way you can make the stuff that you can see, or even planets, just a second, cause enough gravity to keep the Milky Way together. So really, if what we see here is all we got, the Milky Way should have long blown apart, just because it's rotating so fast. So there's got to be something in the Milky Way that glues the Milky Way together, that keeps it together. That is dark matter. Yes, question?
How long have we known that there is that lack of gravity? When did you first calculate that?
Right, the very, very first calculation was done by Fritz Zwicky in the 1930s. He didn't look at the galaxy, he looked at a cluster of galaxies, but he basically observed the same thing. Namely, what is the observation? The observation is that the stuff in the universe is moving much too fast, given the gravitational pull that should keep stuff together, so it should blow apart, but it doesn't. He observed it in galaxy clusters, but the observation in the Milky Way goes back to Vera Rubin. I think that was in the 1950s, and I hope nobody has online Wikipedia and couldn't correct me on that one. No, but around that time is roughly since we know that. So a pretty long time, right? I mean, it's like, wow, that's decades, right? And we still don't know what that glue is. Oh yeah, by the way, super glue, right? That's what we're looking for. The super glue is stuff that keeps the galaxy together. Yes.
Well, recently they have found out that most of the galaxies actually do have, or in galaxies, let's just say that, have a black holes in the middle of them.
Yes. That is correct. That is actually, recently we can argue again what is recently. That's, for the Milky Way, we know that there's a black hole at the center of the Milky Way since more than 10 years already. And we know that because we see at the very, very center, so if we look, I mean, you see it's hard to look because you have all these dark clouds, which is like, you know, like smog in summer. It makes it difficult to look through it. But if you look at the center of the Milky Way, you can actually, now our telescopes are good enough, we can see individual stars. They go around the center of our Milky Way with incredible speeds. It's like slingshots going, those things go around the center of the Milky Way. So again, you can use Newtonian gravity and calculate what that means for the mass that you have in there. And that's why we know that the center of the Milky Way, for example, there's a supermassive black hole, many, well, don't quote me on the number, millions of solar masses heavy, based on basically an observation of the stars as they go around it. So yes, there are lots of black holes. So what you can now say is, oh, but now I add those millions of solar masses heavy black hole to this equation. Does it change anything? No, it doesn't change anything. Why not? Because the galaxy is billions of solar masses heavy. If you add a millions of solar mass black hole, it doesn't make a difference, right? I mean, we are really not talking about a small effect here. We're talking about a huge effect. I'm showing you that in a picture in a bit more quantitative way. And I'm not showing this with the Milky Way, but I'm showing you that with the galaxy M33, that is a member of our local group, so it's our neighbor galaxy. What I want to show you, so it's a spiral galaxy, and we can see that very nicely. That's why I want to show it to you, to tell it, maybe picture how big this effect is. And this is one of the slides which I tell to my colleagues is exactly the same thing. So you have the spiral galaxies. Now what you can look at is as a function of distance from the center. Here you go. This is the radius from the center in some weird units, kiloparsec. That's just thousands of parsec, and a parsec is 3.5 light years. So we go out some, what is that, 70 or so 70,000 light years. And again, by the way, oh, this is something else I want to mention because I see some faces here. That's okay. Okay, 70,000 light years. How big is that? I cannot imagine that. Okay, it is just above my head. Yet I'm working in this field. It's no big deal. I mean, if you ask any politician, you know, who of them can imagine the depth of the United States? You know, how many trillions is it? Whatever. Nobody can imagine that, right? But it doesn't matter. You can still work with it. You can still account for it. You can still live with it, right? So okay. So what that just means is it's a very large radius. But you know, you can see it on the picture. But there was a question here. Yes.
Sorry. When they first I guess discover that there is proof of dark matter.
Mm-hmm. Well, so that depends what you mean with proof of dark matter. The first observation was Fritz Zwicky in the 1930s. The second observation was Vera Rubin in the 1950s. And more observations kept piling up. And it always became more and more observation, never become less. Now, at which point do you call something proof? And of course, we are in the right spot to talk about in the right room, and I'm sure you have talked about a long time, often in this room, about what does it mean, scientific proof, right? At this point, what people say is, most of my colleagues, 99.99% of my colleagues, would agree that yes, there is dark matter. What we don't know is what it is. What we think is missing to really have the final proof, if you will, that really dark matter, this whole ideas that I'm presenting to you are correct, is to really find, is what I'm trying to do, to find these particles that make up this dark matter, right? I mean, I'm postulating here there's unseen stuff. Well, that's, I mean, come on. I mean, yeah, right. So to really believe that, the reason I really believe that is because there are so many observations that all point in the same direction and can be all explained. Like, again, a dozen of different observations. They can all be explained by the same thing. That's just, there has to be some so far unseen stuff out there. But so for me, that would be the final proof when in my detector I find something. Other people have accepted it in the 1930s already and said, yeah, there has to be more stuff. Yes, more questions?
Yeah, so when did they start calling it dark matter?
Fritz Zwicky called it dark matter. Actually, he was a German guy, so he called it dunkle Materie. Yeah. But yes. Yes?
What kind of methodology do you use to look for this dark matter?
Okay, that depends. I'll talk about that at a later point. Unless you ask too many questions, which is great because then I run out of time of that. And then what we do, if I don't get to that, you just ask me that question in the end and I'll show you. But I'm pretty sure we'll get to that.
Okay.
Okay, so what I can do is I can look at all in this galaxy, and this is really just one example. If you can do it with any spiral galaxy in the universe, including our Milky Way, it looks basically the same. What you can do is you can look at the stars, right? You say, okay, there's a little bit of extra stuff in dust, in planets, in black holes. You add all that together, and you say, what is the highest speed that that I could, like on the merry-go-round, that I could sustain based on what I observed before blowing stuff up? Okay, and that's this curve that you see here, and the speed here are quite large. They're like, we're talking about 100 or so kilometers per second. 100 miles per second. These are rather large speeds, okay? But, the sun is flying through the Milky Way with 230 kilometers per second, so that's, 160 or something miles per second. Doesn't make me feel uncomfortable, right? Space is big, space is empty. I mean, chances that we bump into something else are pretty slim, so no worries there. So this is the minimum, that's the maximum velocity that we can sustain. Anything that would be faster than that would make the galaxy blow apart, because that's the only speeds that I can sustain. But that's what we observe is the actual rotation speed of the galaxies. Okay? What you can see is, that's what I meant when I said it's not a small effect. What you can see is that there's a huge discrepancy, right? It's like it's almost a factor 10 in this picture. The galaxy is rotating way too fast. It's what we call a flat rotation curve. You can see that it's basically flat. It's rotating way too fast to really glue it together. What glues it together? And what you can do now is you can say, okay, maybe I just need some additional matter. I need more stuff, right? And you make some idea. You have some ideas about what that could be, and people have some very nice ideas. The simplest idea actually that you could have is you say, okay, you just have a blob, a sphere out of gas, gaseous stuff out of dark matter, which you call a dark matter halo. Okay. If you add just that one, vanilla scenario, it's the simplest thing you can cook up with, right? Just a sphere. I mean, this is what you would say, what could be the velocities that you can sustain, and it fits right smack on. Again, this is not only the case for M33, this is the case for all spiral galaxies that you look at. Okay? So this is by no means the only evidence that we have for dark matter, but it's a very nice one because I think it's very pictorial, right? It's a merry-go-round. And all the merry-go-rounds in the universe, they just go all too fast. And to explain that, why they don't just fall apart, we need extra matter. And I can show you the rotation curve in the Milky Way also. That's exactly the same thing. Again, here the radius and the speed, and you see the speeds here are a bit higher because the Milky Way is bigger. 200 or so kilometers per second, that's where we are. What you also can see is the arrow bars on the outskirts are larger. It's more difficult to measure. To the inside of the galaxy, there's more stars, so we can measure more easily. But what you see is that, the rotation curve is flat. Mainly, of course, you see that it doesn't go down as we would expect it to do. Oh, here's another thing just comes to mind. If you look at the solar system, if you have some astronomers in the audience, you know that the further out you go in the solar system, the slower the planets move around. Right? Pluto is really, really slow. Oh, sorry, it's not a planet anymore. But, you know, I mean, the Mercury really whizzes around, while the further out you go, the slower you are. That's what I showed. That's exactly what you see here is, right, the further in you are, the faster you are, and if you go further out, you get slower. But you can see, again, this is not what is happening in the Milky Way, again, because unlike the solar system, we have all this dark matter all around. Yes, there's a question.
So there's a kind of englobement?
Yes.
Can you explain how gravity in an englobement works to contain the centripetal force and so forth?
So there's some if you work out the equations, that's actually quite odd. If you are in the center of Earth, the stuff that is outside of you doesn't matter, and the stuff that's within you is just as if it were a point at the center. It's because distances just cancel out because the problem is so symmetric. That didn't. Okay, let me try again. Okay, so in effect, what happens is you have to look at from our point of view. There will be some matter to the left, some matter to the right, but if there's an equal amount to the left and there is to the right, that will just cancel out. Okay? So I can do that in all directions. So really what I need to just work out is in a spherical blob, what is the net force? Okay? And you can work that out. The net force just goes to the center of that blob. Okay? Maybe that's a better answer. I'm not sure. If not, you have to
Sounds like we'll just have to get to the equations.
Let me see. Okay, so let me see. Can I do that better? No, I can do that better. So you have this. You are embedded in a sphere. Okay. So okay. Let me see that I get it right. You are your son. Okay, and Mike, right? Steve, sorry. And Steve, who works so fantastically with the computers, thank you very much. He's the center of the universe. Well, no, but he's let him be the center of the galaxy, right? And then you have now the spherical cloud around him, not around you, but around him, a spherical cloud of dark matter all over the place, right? So all those people sitting all over, and you got some people behind you, some people left, right, okay? But then the friendly lady in the red shirt to the right of you, and the gentleman in the black T-shirt to the left of you, they will both pull on you with their gravitational pull. They'll just cancel out. You know, you're not moving. If she pulls you, he pulls you, I mean, where do you go? You just stay where you are. Same thing happens in most directions. What remains, if there's a spherical blob around him, is the only thing that can remain is a net pull towards him. Because there's so many people, more people sitting on this side, well, if you imagine, you know, the room a bit bigger, they will all pull you towards this direction. Well, behind you, there's not so many people. They cannot counterbalance all those people. So you won't go right, you won't go left, you won't go up, you won't go down. Actually, you will just go towards him. Which is exactly what we need because we have this merry-go-round, right? You need to hold on to him.
So the further you are out on the sphere, the more pull there is in
right,
the other direction.
Right, which is also what you need because the further out you are, the faster you are. Right? That's exactly what this curve means. Yes, fantastic. Yes, another question.
I have kind of a scale problem. As I understand it, the universe is expanding.
Yes.
And that you're talking about things staying together.
Right.
Is this a local phenomenon? Is that?
Okay, so on the scale of the, I'm on slide 8, if somebody can remember that. The scale of the universe on, the expansion of the universe when we come to when we talk about the rotation curves is negligible. It just doesn't matter because the universe is so big. If we want that to matter, what we have to go to is we have to go through intergalactic distances. Okay, so we have to go to bigger scales because the expansion of the universe is really something that matters at large. So you have to go at large distances. That's where it matters. Okay, so let's go at the next best large distance. That would be our local group again. So here's a picture of the Andromeda Galaxy. There's a picture of the Milky Way. How do you take a picture of the Milky Way? It's of course not a picture of the Milky Way, it's a random galaxy. Okay, and you see it's just a slide I I tell to colleagues, so there's lots of equations. What you can do is you can just again look at the Andromeda galaxy and count stars, right? It's very tedious work, you need lots of students to do that, but people do that. And you can look at the Milky Way and you can count stars. And then you account for planets, gas, dust, all that crap, you add that all up. What that gives you is, again, based on what you see, it gives you a gravitational pull of the two galaxies together. Okay? In particular, the pull that you calculate is that you would expect from 10 to the 11 solar masses. Okay, 10 to the 11 suns. Okay, big number. That's all that matters. Okay, come on, who cares? Big number. At the same time, what you can observe is that the Andromeda is actually on collision course with the Milky Way. No big deal. It'll take a couple of billion years, right? But yes, indeed, in a few, I don't know, 100 millions or billions of years, the Andromeda galaxy will collide with the Milky Way. Doesn't actually matter because there's mostly nothing in the universe anyway, so we'll just go right through each other. But anyway, so what you know now, and that's where your question I think comes in, is you know that this gravitational force, because they move together, has to be stronger than the expansion of the universe. Right? The gravitational force has to be able to overcome the expansion of the universe, because there's all this space in between those two galaxies which tries to drive them apart because the universe is expanding. Right? So what you can do, because we understand the expansion of the universe rather well, you can calculate what is the equivalent force or the equivalent mass of the expansion of the universe, and you find that if you want to overcome the expansion of the universe, you need something like 10 to the 12 solar masses. Okay? And again, what that is to say, there's no big, already now it shouldn't be any surprise anymore. Well, yeah, that's fine. We know that there's 10 times more mass in those galaxies. I just showed that to you on the rotation curves. We know there's 10 times more mass in the galaxies in some dark matter or whatever than there is in visible stuff. So yes, it's perfectly fine that those two galaxies can overcome the expansion of the universe. Right? Does that answer your question?
As well as a lawyer can understand the physics. Yes.
Okay. So about those numbers, don't worry. It just means small number, big number. Yeah. I was on slide 8. I remember that myself. That was as much local from the motivation why we believe that there is dark matter as I could go. Okay. So I want to pause here a little bit because I want to make sure that you understand where we've gotten so far. Just by looking at our Milky Way, goes around too fast, so we need some glue to glue it together, centripetal force, right, merry-go-round, and we don't see that stuff. It has to be something unseen. I want to take that a step further, and I want to go to larger scales. Right? We already went one step further. We went this intermediate step between the local group, between the galaxies and our Milky Way and the Andromeda galaxy. Let's go even further. Let's go to what we call clusters of galaxies, because there's something nice that we can do there. But to do so, I need to explain to you something that is a bit an odd effect, which is called gravitational lensing. And why I wanted to pause here is because if you have never heard of gravitational lensing or clusters of galaxies, I'm afraid that what I'm going to tell you now may sound a bit weird. And you know what? It is weird. It really is weird. Okay? So, but bear with me and I'll see whether we can get there. And again, if you don't understand what I'm saying, well, we need to talk about understanding. If you are not able to grasp how weird a place the universe is, rest assured I can't either. But if you don't get what I'm saying or I'm trying to say, then please ask, okay, by all means. Good, so this is how gravitational lensing works, and this has, at first, well, okay, so this is what it goes. So here we are, this is Earth, okay? And suppose there's some galaxy, or it could be some star, something far, far, far away, okay? Also, let there be some mass, some stuff in between us on Earth and the galaxy which is far, far away. Now, Einstein's theory of general relativity tells us that mass bends space. Okay, that's the point where everybody should go, woo! Certainly I do, mass bends space. Don't worry, just picture, instead of space, picture, a rubber surface or a trampoline, because that's something you can bend, right? That's what's indicated here by the curved line. And by the way, it's another one of those things, Einstein's theory of general relativity. I hate it. It's a terrible misnomer. It should just be called Einstein's theory of gravity. That's all it is, right? It's just what Einstein figured out would be a nice description of gravity. So just whenever you hear that general theory of relativity, just, yeah, that's gravity. Okay, so now what light does is this galaxy sends out light in every direction, right? It sends light out towards the gentleman here and you here in the green shirt. And the light will, that's a property of light, it will do exactly the same as a billiard ball would do on a trampoline. It would just go in straight lines, and if there is a dent, it would follow the dent. Okay, and if you kick it faster or a bit further away, it'll curve a little bit less. But if you kick it right on, it could actually even spiral in. Okay, that's what would be a black hole. We don't have that here, so don't worry about that. But what you picture is the light that is being sent out by the galaxy just behaves as billiard balls. So what you can do now is because you can bend light, yes, you can bend light. Well, everybody who has glasses knows that you can bend light, so it's no big deal. Space can bend light. What you can do is you can now, from Earth, I can look towards that galaxy. Okay, and the fun thing here is that light that is sent out that would normally not reach me because it's sent out to the side, because it's being bent, can still be bent towards me. Okay, this is why this is called gravitational lensing. Because what it does is, in effect, it means that from this galaxy, which is far away, we can see more light that we usually should see given how far it is away from us. Right? So that's why we lens it. It's basically a magnifying glass. It's very good. We can look further into space. Also, what we can do with that, we can use that as a probe of the mass in between us and the galaxy. Okay? Because the more stuff there is, the deeper that dent in the trampoline gets. And therefore, the more light we will bend over, and therefore the brighter this galaxy will look like. Also, it will become distorted. Okay? So if I look at that galaxy, I can tell something about the mass between us and the galaxy. You see where this is going? I have a probe for mass that has nothing to do with whether I can actually see that mass here or not. I just need to see a galaxy which is behind it. That's fantastic. That means we can look at the universe and we can look where is the mass. Even if it's dark matter, it doesn't matter. The gravitational lensing will still tell us. Does it make sense? No questions there?
Oh, sorry.
Yeah.
So when you sit here from and make an observation, right, you can only see the effect, the final effect of how that light was bent. You can see where it was bent.
Right.
So how would you compensate to find out the original? Would you use different spectrums or X-rays to determine the stuff that would be affected differently by a gravitational force to determine where originally it came from?
Okay, so there's a few things that you can do. That's an excellent question. How do I know that this is happening? I would know that, for example, because this guy here on Earth, he can't look in this direction and see that galaxy, but he can also look in a totally different direction and he would also see that galaxy. So actually what we get is sometimes, I didn't bring a picture with me, I'm sorry for that. Sometimes you see those pictures of Einstein rings. You see the same galaxy if you're looking in different directions. And you can tell that it's the same galaxy because it has the same spectra, the same distance, the same, it looks the same basically, right? So that's a way that you can tell that this is really happening. That answers the question. Yes?
Is the amount of distortion equal to the amount of mass?
Yes,
okay.
The amount of distortion is, well, is
yeah.
related, right? So once you know how much you distorted, you can work out how much mass there is. Okay. Let's apply that as a tech. I mean, that was actually brand new. It was a great discovery when it was first discovered. I don't know, 30 years ago or so, perhaps. Today we are beyond that stage. We actually accept it as a tool to do astronomy with. Isn't that great? I mean, I mean, relativity, right? I mean, it's now 20 years old. It's really, it became a tool to use to do other fun stuff with. And here's a fantastic example where we can use that well, very prominent example to learn about dark matter. It's called the bullet cluster. Why will become apparent in a second. This is a picture taken by, well, I think it's by the Hubble telescope. Actually, I'm not sure. No, it's not the Hubble telescope. I don't know which telescope. Some telescope. Optical light, so this is if you had better eyes, and this is what this area of the sky would look like. And if you look at it with an angle, you can see that there's all those white areas, all of those blobs are all galaxies. Okay, wow, there's lots of them, right? But you can also see there's a blob of them. There's more somewhere around here. You can see those. If you're good, you can also see that there's a bit more galaxies over here. That's because there's two clusters of galaxies. Galaxies are like humans. They like it to be together. So of course, because of gravity, they like to cluster together. So they don't usually come alone. They come in big families. Also, our family is called the local group. It's also a family. Oh, here's another side thing. I'm getting sidetracked, but I just like it. If you look at a picture like this, how do you know what is a star and what is a galaxy? There's always one thing to tell us the two things apart. Does somebody know? Do we have an astronomer here?
The star twinkles.
Yes, yes, absolutely. The star twinkles, and in the picture, what that means is that the star has those spikes, while the galaxies don't, because they are point-like. The galaxies are, have some size. Also, the amount of rays depends on the telescope, because that really what you see is a diffraction pattern on the secondary mirror of the support structure. So okay, so you can tell by how many spikes there are. You can tell which telescope took it. Anyway, so we have those two clusters of galaxies. Now, an additional piece of information I need to give you, but then we finally get to the fun bit. An additional piece of information is that if we have anything like the Milky Way, I should have said that probably a bit earlier. If we have something like the Milky Way or a cluster of galaxies, the material that we know, protons, neutrons, electrons, matter as we know, the periodic table of elements stuff, it's only a small fraction of that is actually lights up as stars. About 10 times more matter than we see in stars is actually in dust, in interstellar gas. Okay, and another 10 times more is in dark matter. So really, if you look at this, if you really want to know where the visible matter is, all the elements that we know, everything that we know of, you have to look at where's the gas. You can do that because in those clusters, the gas is actually it's like those here. Yeah, it's like those fluorescent lamps. It's ionized. It's a plasma, so it glows in X-rays. And here's what you can see. You see two blobs. There's one blob is here, and another blob is here. And that's because there's two blobs of galaxies, right? Actually, what happened? You see, this guy has a shock front. Right? It's like a bullet going through a layer, which is where the cluster got its name from. What happened here is some, I don't know, 100 millions of years ago, probably, that those two clusters of galaxies, they went right through each other. And when you do that, then you get a shock front, right? You get the gas that goes through each other from the smaller clusters being shocked. You get this bow wave, basically, right? Like a ship going through it. Okay, so because there's so much more gas than stars, this is where we would expect, this is where we see most of the mass, centered here and here, okay? Now what I can do is I can use that method of gravitational lensing, which I explained in a second minute ago, probably 3 minutes ago. I can use that method and ask it, where does gravitational lensing tell us where all the mass is? Okay, and this is what gravitational lensing tells you. It's overlaid not as a funny picture map, but it's like as a contour line. If you look at maps, gravitational lensing tells you based on all the galaxies that are in the background. You look at all of them and you map it out very detailed as different positions. There's a huge blob of mass here, and also a blob of mass, but it's a bit smaller, is over here. And what you can see is that these are offset. Okay. What that means is that most of the mass in this cluster is actually not where most of the visible mass is, where most of the gas is, but it's offset. How can we understand that? Well, this is something that tells us something about, well, we know by now that there is dark matter, right? This is something that tells us something about dark matter. And what it tells us is that if you have two clusters of galaxies going through each other, then the normal matter that we know, the gas, is being shocked, is being slowed down. There's something like friction, right, that slows it down. Whereas the dark matter of the two clusters just goes right through. It is not being slowed down, and therefore, by now, it is a bit further away, right? While the gas is lagging behind because it got slowed down. So this is a beautiful observation that came out in the 2006, I think it was, about again a total different scale, a total different tools, and total different environment where we know that there is dark matter, we can even see it happen, like dynamically, right? We can see that it goes through each other just like nothing. So it tells you that dark matter is something that is interacting only very feebly. It doesn't like to interact very much, at least much less than, you know, gas, air, you name it, the stuff that we know. That's a question.
Is dark matter affected any less by gravity than visible matter?
No, we think that dark matter is affected in the exactly same way as visible matter by gravity.
Okay.
Which is, so far, the only way that we know about dark matter. Through gravity. It's the only way we know about it.
If it's affected by the gravity, then this kind of stuff shouldn't really happen.
Why not? Why not?
Well, because if the dark matter is proportional to the gravity, then the clusters should keep the dark matter more in tune with where they are.
But wouldn't the dark matter
but the dark matter dominates the cluster. There's about
There's
10
so much
times,
more
10
gas,
times more.
yeah, okay,
so the gas
okay.
really, you know, it's just
Yeah.
it tries to follow, but it can't because there's a friction.
So would it then orb around the galaxies too?
Say that
The
again.
dark matter, is it doing those circles too?
Well,
Or not?
we don't think it does. We don't think it does. We don't know for sure because we can't look at it yet. But we don't think it does. Yes.
So kind of from that, see, the dark matter would interact with regular matter equivalently as far as gravity.
As far as gravity, but
when it goes through there, what the effect of dark matter passing through dark matter, there would not be as much of a gravitational effect between that dark matter.
No, the gravitational effect is there, but if you have something like friction that's so much stronger than gravity, luckily, because that's what keeps you on your chair, right? The friction that keeps you on your chair is so much bigger than the gravity, so you don't fall off. Gravity is not, friction is much more important. If you have friction. Dark matter doesn't seem to have friction, it just goes right through each other. Looking at the clock, what I want to do is I want to skip ahead a little bit, and we can talk a little bit about cosmology later if you want to. What I try to at this stage now with only two or three examples give you an idea why we think there is dark matter, and let me see. How are you guys? I mean, this is now 45 minutes already, so I would do another 15 or 20 minutes, and then, you know, we make a break and people ask questions, and we can talk about cosmological stuff, the cosmic microwave background later also if you want. Still, you know, just to keep it a bit compact. So take my word for it. Yes, there is dark matter. Okay. What do we know about dark matter? What properties could it have? Actually, let me skip that. We know that dark matter has to be some kind of a new particle that is invisible. And that is, if you first think about it, somebody like me now coming off, who would like to catch that, right? Who would like to find it, it can be a very frustrating thing. But it shouldn't be, because we can take a historical perspective on the topic and see what we learn from that. And when we do that, we find that, for example, in 1844, Bessel predicted the companion of Sirius A, based on movements of Sirius, purely gravitational evidence, and indeed Clarke discovered Sirius A in 1862. Okay. 1845, Adamson and Le Verrier predicted, again, only using Newtonian gravity, based on the motion of Uranus that they observed, that there has to be an eighth planet. And indeed, there was a fantastic success of physics. Johann Galle, he took their prediction about where this planet should be and roughly how bright it should be. And on the very first night, on the very exact spot that theory predicted, the eighth planet, Neptune, he found it. A great success of science. Again, based on purely gravitational evidence, we found something new. You can also go to particle physics in 1930. Pauli predicted a neutrino based on his observations at the time of the beta decay, radioactivity, and he even wrote that. He said, "Oh, I did a terrible thing. I invented, or predicted, if you want, I invented a particle that we will never be able to detect." Boy, was he wrong. He was proven wrong by Cohn and Rines in '56. They got the Nobel Prize for that. Of course, Pauli got it also. They discovered the neutrino, and yes, there it is, right? And today we do physics with neutrino. We use neutrinos to learn about the sun. We use neutrinos to write crazy articles about them going faster than the speed of light. By the way, quick updates. No, they don't. We all knew it all along, but no, they don't. So really, we should be motivated, right? We should not be frustrated about that at all. We've done it in the past many times. There's actually some other examples also. We talked earlier on about the black hole in the center of our Milky Way, right? We can't observe it, but just because of gravity, we know it has to be there. So we can do that, right? Now, if you do that, what you need to do is you need to have some idea about what this particle that you're looking for could be. If you have no clue, then you don't know what kind of detector you want to build. Here's our current best idea, which is by no means to say that it's the correct idea. The point is, once you come to the point that you say, oh, there is all this dark matter and we have to find it, you need some idea what to build. And this is the best idea that we have at the moment, is that dark matter could be a thermal relic particle, meaning it could be a particle that at the early times of the Big Bang was constantly produced and annihilated. All particles that we know were at the early times in the Big Bang constantly produced and annihilated, right? I mean, because the universe was so dense, so hot, they would constantly smash into each other, create new particles, and new particles, they would again create the old particles back and forth. Huge soup. That would happen all the time, and all the particles that we know today did that. So, you know, why shouldn't dark matter do that as well? I mean, does it have to do that as well? No, but it's kind of reasonable, right? I mean, every particle does that. Also, there is the other question could be, how heavy could that particle be? And there is indications if we look at all the particles that we know, that something gets wrong once you go to masses of, say, you know, a typical element, like a few hundred or so of proton masses. Once you have a single particle that is as heavy as 100 protons, in the model that we have that describes particle interactions, things turn weird. Okay, there's a few problems that you have, and you can reconcile that everything at once if you just assume that there's one new particle that has, you know, masses in around this region. So hey, this is great, because there's now all these astrophysics guys that say they want to have new particles, and there's all those particle physics guys that say they want to have new particles, and actually this particle could be the same particle. If that's really the case, that would be fantastic, right? It would be not only solve all the different observations in cosmology, and I only talked about 3 out of a dozen, but it would also solve the half a dozen or so of problems that particle physicists have. Those particles are called weakly interacting. Well, we know from the bullet cluster, right? They are not interacting a lot. They would interact weakly. And massive, because 100 protons is heavy, right? Massive particles, or WIMPs for short. This is actually quite a, why are they called WIMPs? It's a stupid name, isn't it? And at the time, this was in the 80s or so, the leading candidate for dark matter at the time, people said, oh, it could be, you know, stuff like Jupiter's, like planets. You know, I wouldn't see those. The bullet cluster, for example, tells you why it cannot be planets, because they probably would bang into each other also. And there's cosmological observations that I didn't talk about that also say that. So those were abbreviated massive compact halo objects, or short, machos. At which point then that was actually mainly female by some weird coincidence. Maybe female particle physicists and cosmologists cooked up this concept of the WIMPs to counterbalance the machos. That's where that's coming from. And if there's really those new particles, that's fantastic, because we have 3 channels of how we can detect them. I'm so running out of time. Hey, how long are those talks usually, right? I mean, it was this famous guy, 1 hour, right?
Usually we make a program, cut it off at least in 2 hours, but you don't have to lecture an hour, you know, by the time you have your question and answer and all that. So. Okay. So you're fine.
I'm happy if you just keep going.
Okay, so I'll tell you about the 3 mechanisms. We'll make a break. We'll turn on the light. We'll have a Coke, and then we'll just keep on going. How's that? Yeah. And then if you can't hear me talking anymore, you can just go home. That's fine. Okay. So here's I want to introduce you to a tool of particle physics. If you have a theoretical particle physicist, you know those crazy guys that just sit in their office all day and crank away with computers or pen and paper, a very important tool for them is, well, of course, you know, integrals, equations, all that stuff. But even more important than that, the most important tool for particle physicists is what is called a Feynman diagram. And that's a Feynman diagram. I thought I wanted to introduce you to the single most important tool of particle physics, theoretical particle physics. What that means is, it means that there's you know, some particle, call it F, some standard model particle, proton, whatever, electron, muon, you name it, that comes in. There's another one that comes in, and they go, whoa, we don't know what's happening there. But what comes out is a dark matter particle. We call that with the Greek letter chi. That's just a convention, and another particle that comes out. Okay. So what you have there is you smash two particles into each other, and two dark matter particles come out. Okay. That's all that theoretical particle physicists do, is they try to work out the integrals of those things. But you can do it also, right?
Why is the arrow going the other way?
Oh yeah, somebody had to ask that, right? That's because it's an. Okay, you asked for it. I tell you the answer. That's because it's an anti-particle, which is why I got the bar over it.
Yeah.
Which means it's the same particle, just with the opposite charge. We think dark matter is not charged, so if you have 0 and you take the opposite charge, it's still 0, right? So it doesn't make a difference. But the fun thing is, and here you come, you love this one. The fun thing is that for, in this diagram, time goes that way. The fun thing is for antiparticles, time goes backwards. Yeah, you didn't know that one, right? Well, you asked. So how can we search for that, right? If we have those particles that in the early universe constantly particles were smashed into each other, produce those dark matter particles, and vice versa, how can we look for that? We do that at collider searches, and you have heard of the LHC, the Large Hadron Collider in CERN in Switzerland and France. What we build is those huge devices. You see some people standing here, right? This is a picture of the part of the barrel of the CMS detector. What you do is you smash protons into each other, right? Just the plot that I showed you. You smash two protons into each other, it goes, we don't know what happens. But what comes out is two dark matter particles. You look for that with those machines, okay? The actual data, if you're interested what the actual data looks like that. You observe the brown stuff, and if those particles, you would observe them in those dark matter particles, you would expect the yellow curve. But you see the white data points follow the brown expectation and not the yellow one. So no dark matter signal so far. Okay, so here's yes?
I'm sorry. When you say that two dark matter particles come out, are you saying that there's one dark antimatter particle and one regular dark matter particle?
Yes.
Doesn't the antimatter one just...
You know, it could be, at this stage, it could be totally the same particle. It could be that they're indistinguishable.
Okay.
For the photon, for example, that's the case. Photon, antiphoton is the same particle.
Okay.
There's other particles where this is the case. Neutrinos, for example, they also don't have charges. It's a question that is actually actively researched, and people build huge experiments to try to figure out whether neutrinos are their own antiparticles, whether that's the same particle and antiparticle. So it could be the same. There might. So it's a technical detail. Huh? I want you to skip it. It's a technical detail. Ignore it for all practical purposes. The great thing about those diagrams is you can turn them around. Right? Wow, this is deep theoretical physics that we're doing here. It's not trivial, but if you do turn it around, what you get is this diagram. If this exists, you know that this one has to exist as well, which tells you that you can smash two dark matter particles into each other, and what comes out is two standard model particles. In particular, actually what you would get is you would get, for example, two gammas, meaning two photons, meaning two flashes of light. Or you could get a neutrino and an antineutrino. You could get an electron and an anti-electron, which we call positron. You would typically get pairs of particles and antiparticles. Okay. And you can search in particular for the antiparticles. The current status of the field is undecided, I would say. Maybe a nice word of saying that. There's lots of data. Here is shown as a function of energy. We can search for, in this case, for example, positrons. This is what we would expect. I mean, there's this new Pamela satellite, which observes that at high energies, we see more and more positrons than we would expect. Those could come from dark matter particles smashing into each other, annihilating, that's the technical term, meaning creating those electrons and positrons. And indeed, we would expect that. The problem here is, first of all, we would expect it to turn down at some point because of energy conservation when you get to the mass of particles. Detail again, you would expect it to go down, and there's new data that tends to go further up. The other problem is, when you look at that, how do you know that you're not just looking at astrophysics? I mean, who tells you that there is not just some pulsar, some astrophysical object somewhere in the Milky Way that creates those positrons, right? It's hard to say. A similar problem here happened with the WMAP haze. This is the Milky Way looked at in some weird wavelength, and we blinded out, we blacked out all the, you use a text marker, black text marker, and you wipe out all the areas where there's lots of stars and stuff, because there's foreground, you don't know. You look at the background, what you find that there's some emission centered at the Milky Way, at the center of the Milky Way, which is called the WMAP haze. That could be photons coming from dark matter annihilation, or electrons that the magnetic field circle give off photons. Either way, but then again, is it that? Or isn't it just some outflow from the galactic center? I mean, it's a messy place, the galactic center. There's black holes and all those things. So while in theory you can search for these diagrams, in reality it's very messy because you have lots of astrophysical background processes that you have to disentangle and you have to find a way around. So at this stage it's certainly unconcluded. The third one, and that's what I'm doing, is, hey, we just said that we can turn Feynman diagrams around. That was a question? No? Just scratching? That's also fine. You're allowed to do that. It's not an auction. Yeah, that is scattering, and that is, hey, we said we can turn them around, so let's turn it around if this one exists. And the only assumption I made is that we have a particle that in the early Big Bang, in the early times shortly after the Big Bang, in the early universe is what I wanted to say, was, as all the particles in thermal equilibrium, constantly being produced and annihilated. Then you know, because you can turn those Feynman diagrams around, this diagram has to exist. What that means is that you have a dark matter particle coming in, dark matter particle going out. That's now where the arrows are important, right? And a standard model particle coming in, standard model particle going out. That's just scattering, right? All that means is that a dark matter particle can bounce off a proton, a nucleon, an atom, you, me, whatever, and kick it a little bit, right? That's what this means. So I think this is a nice plot here. To end at this stage. The take-home message is, we know there's, at this stage, the take-home message is, we know there's dark matter. We have some ideas what it could be, and they actually tell us a lot. Because you see, just this one idea saying it was a particle that was produced and annihilated all the time in the early Big Bang, gives us all those different tools, all those different sets of experiments with which we can search the same particle. And if we eventually manage, then and they all give the same coherent picture, we could really say we have nailed dark matter, right? If all those experiments see the same thing. I would suggest I'll answer the question and then we have a break. After the break, because that's what I do, I would talk a little bit about how we build those detectors that try to scatter them and actually catch them in a laboratory. Because we have seen that there's dark matter in the Milky Way. Right? We are in the Milky Way. Hey, surprise, surprise. So we can search for dark matter in this room, basically. And I'll tell you how we do that. But there was a question.
If we have observations that show dark matter is not interacting with the things we see, how would that bottom diagram work?
So what that means is the observations, yes, it's an excellent question. It bothers me every second night. So the observations that we have are astrophysical observations. And what they do is immediately they tell you the probability for this to happen has to be small, right? Dark matter may in principle do that, but if it does that, it doesn't do it very often. Okay. So what you have to do is you have to build extremely sensitive detectors now. And again, I'll tell you how we do that. So yes, exactly. It tells you right away that this cannot be a strong interaction. It cannot, for example, be an interaction like like my eyes have with the light of the beamer because it blinds me, right? That all the light that comes in my eye just interacts with it. It cannot be like that because all the dark matter that we encounter on our way through the galaxy doesn't interact with me, otherwise we would have felt it. So yes, it gives you directly an upper limit on the interaction.
But the same thing happens with neutrinos, right? They don't interact.
Right. Oh, you don't have to go to neutrinos. You can do, I mean, it's just radioactivity. You go to the dentist and you have an X-ray. An X-ray goes through you most of the time, except if there's a crown in the way, then it gets stuck, and that's why the film on the other side of you is being whitened there, or stays white and doesn't get like whatever. Right, so I mean, radioactivity particles do that all the time. There's probabilities that they go through something, and depending on what kind of particle you have, and what kind of target you have, they go through it easier or less easier, right? I mean, X-rays are a fantastic example. They go easily through skin, not so much through bone, and not at all through a gold crown. Yeah. Okay, let's have a break here. Thank you. Okay, so I'll turn off the light again.
Yeah.
So
Okay. Very good.
have a good night. Okay, so this is where we were, right? So we said, okay, this is a very nice, a very simple idea for dark matter, gives us all those possibilities, and I want to talk a little bit more about the last one. Okay, so two things maybe which came up during the discussion during the break. Number one, we know that dark matter has to be something completely different from all the things that we know otherwise. Like all the periodic table of elements, all protons, neutrons, electrons, muons, tauns, neutrinos, whatever you name it. All those things cannot be dark matter. And why do we know that? Well, because dark matter behaves differently than all the stuff that we know, right? So it has to be something else. That's that. And the other thing is somebody was asking whether I would talk about dark energy, and no, I'm not. And the reason for that is because, honestly, it has nothing to do with each other than having the same first word in the name. So it's really two different things. Okay, so we are on Earth, and we, together with the sun, fly through the galaxy, right? So we have this dark matter all around the galaxy, and the sun flies through the galaxy rather fast, 230 kilometers per second. But then there's also Earth, which goes around the sun. That's actually quite nice, because what that means is that we go a bit faster in summer through the galaxy, and a bit slower in winter. Does it make sense, right? Just depending on whether we go with the sun through the galaxy or against it. And that's a great feature that we can exploit in any detector, because it means if I want to look at, if I have a signal in my detector, a clear prediction that I have is that you have to see this modulation. You have to see, because we go faster, a little bit more of the dark matter, we encounter more dark matter in summer, and a little bit less of your signal in winter. Right? It's a great thing to look out for. Now, if you have, just generally, if you want to build a particle detector, and you have a dark matter particle, a WIMP, or any other particle, alpha, beta, gamma particle, you name it, neutrino, whatever, it comes, and if you're lucky, it scatters in your target. It deposits a small fraction of its energy. You know, it just rubs a little bit. Then just very generally, you have three channels in which you can try to well, detect this little bit of a friction. One channel is, you know, when you rub your hands, you get heat. Right? A fancy term for heat is phonons. You can detect it by sticking a thermometer on your detector. That's one way. If you have a cat fur and you rub that, right? You know, you can make your hair stand. So you get ionization. You get electricity. That's another thing you can look for. If you have a semiconductor, for example, you can look for a charge signal. Or that's a little bit less known. There's some materials which have the property that they scintillate, meaning they give off flashes of light when they are hit by a particle. And there's a few oddities which don't quite fit in. Not surprisingly, all those different interaction channels are covered today by a large variety of detectors and experiments. All these are the names of various experiments that are used to try to find dark matter. Okay? Now, I have no hope of explaining all of them to you, and frankly, I don't even want to attempt to even do so. I'll be very egocentric, and I will just talk about the experiment that I'm working on. That's a Xeno 100 experiment, which exploits a combination of the scintillation, so the flash of light, and the ionization, so a little bit of a charge signal. And I'll explain to you that one detector in a bit more detail. If you want to know about some of the other detectors, I have some slides about them as well, and we can talk about them. But I think we'll do that after the official part here. The collaboration I'm working on, the whole field is really organized in collaborations, all those experiments. And the experiment that I'm doing is, more than 60 scientists out of 15 institutions all across the globe, from UCLA, Los Angeles, Purdue here, lots of members in Europe, and all the way to Shanghai. And if you look that up in time zones, makes for some very fun telephone conferences, which are like at 11 p.m. or midnight for the guys in Shanghai, and at 7 a.m. for the guys at UCLA. At Purdue, we're kind of nice because it's 10 a.m. in the morning. You see. We get that nice. If you want to do an experiment like that, what you better want to do is you want to reduce your background. Right? It's all about signal to background. We know, because there's I mean, we haven't found dark matter yet. So obviously it interacts very rarely, right? If it would have been easy to find, we would have found it 50 years ago. We didn't find it 50 years ago, so it's hard to find. So what we have to do is we have to reduce the background. I have to get rid of all the particles that I do know, okay? We do that in steps by step, so we are sure we don't overlook something. We did that since 20 years. This, what I'm presenting to you now, is the level that we are at the moment. If you have a detector for any particles here on the surface that you operate, most of the particles that you see, most of the natural radioactivity, and yes, there's a lot of natural radioactivity here, okay, be not mistaken. Natural radioactivity in general is just normal, it's everywhere. Most of it is actually coming from space. It's called cosmic rays. You may have heard of solar wind. That is part of cosmic rays, a small component. Most of it is galactic, comes from other stars. So you need to shield that. And to shield that, okay, so let's shield radioactivity, right? To shield an alpha particle, do you know how much, what do I need?
About a sheet of paper.
A sheet of paper, exactly. If I want to shield a beta particle, what do I need?
Aluminum foil.
Yeah, well, yeah, that or aluminum foil is fine, or if you even have just a pullover, that's good enough. If you want to shield a gamma particle, well, that's when you go to the dentist, right? He gives you the skirt of lead, and depending on the energy, you want to have that lead being thicker and thicker and thicker. Now, cosmic rays, they contain also particles which are called muons. Muons are terribly hard to shield. If you want to shield them, you need tens or hundreds of, I was saying meters, but let me say yards, of lead. Right? Now that's very expensive, so what you do instead is you go underground. And this is what we do with all those experiments that I showed in the previous slide, is we go to underground laboratories. This particular one is the Gran Sasso Underground Laboratory in Switzerland, what am I saying, in Italy, which is located a mile deep underground in a mountain. And this mile of rock is used to shield the muons, so to have less background, right? I mean, if you want to search a needle for a needle in a haystack, I mean, one way to do that is to make the haystack small. Huh? So you get rid of all the hay, and that will make it easier to find the needle. So when you are a Roman and you want to go for a swim on the Adriatic Sea, you take the highway all across Italy, and this brings you past the mountain town of Acerci here on this highway. And the highway needs to go across the Gran Sasso mountain range. It does that by a 10-kilometer long highway tunnel, which is, you know, what is that, 6 miles that is drilled there. Anyway, there's a question.
Yeah, how do you know that the mountain range or the
doesn't shield dark matter?
Doesn't shield dark matter.
Yes,
right.
exactly. So how we know that is that we searched for dark matter more than 20 years ago on the surface, and we didn't find any. So we started adding a little bit of layer of lead, and we still didn't find any. So I mean, if you look for needles in a haystack, if there's lots of needles, you can find them in a big haystack. If you don't find them in a big haystack, you make the haystack smaller until you find them. Does it make sense? So yes, if we would just start now underground, that would be foolish. But we have started on the surface 20 years ago. You do the easy things first, right, before you do the hard things. We actually like this laboratory a lot because there's a lot of infrastructure that you need to run such an experiment. There's a lab and other stuff which make life easier. So this is a picture of the whole thing. There's a cross section of the mountain, and you see there's this highway tunnel. And underground labs are horribly sparse. There's not many of them, and the reason for that is because they're very expensive. Highway tunnels are drilled all the time, but scientific underground labs hardly. And the only hope of getting one is if somebody drills a tunnel anyway, or somebody has a working mine anyway. Then you can maybe ask in this particular case to have the drill, you know, go off at an angle and then you have your underground lab. The underground lab is, here's a sketch, is the 2 highway tunnels, and then it consists of 3 major halls. The particular experiment that I'm working on is in the corner here. So the way you need to picture is has anybody seen The American? It's a movie with George Clooney. Right, I mean, in the opening credits, there's the whole opening credits, which are horribly long. This guy drives through a tunnel. And then at the end of the opening credits, it just gets all white because he's driving out of the tunnel. He's driving through that tunnel, okay? 6 or 7 miles long tunnel, looks like that, and you just drive there and drive there. And you know, it's really long, 6 or 7 miles. It's just straight, and you know. But then at some point, halfway in, there's suddenly an exit. It's like, I mean, I don't know, if you're a tourist and you drive past there, I mean, what do you, an exit in the middle of the mountain, right? But there's an exit. There's a doorbell. You can ring the doorbell and say the magic words, and then you have a stainless steel gate, which is open here. In this case, you see the background, which then opens, and it really, seriously, it feels like in a James Bond movie every single time. So it's a stainless steel gate in the middle of the mountain, and you drive in there, and then where you are in the largest underground laboratory of the world. This is a picture of one of the 3 big halls. This is a human being here. So they really are large. That's when they were excavated. Now, of course, they are all covered. This is a bit of an older picture, but anyway, you can see these huge halls. You can play tennis, soccer, or whatever you want to, or you can put experiments in there which search for rare particle interactions. That's the kind of experiments you put there, right? Because that's it, that you want to make the haystack small. So experiments that are in there, it's a great place. It's a great community. It's very international. It's a very also. It's all particle physicists and some nutmegs, but it's really it's nice because they come from different fields. So, for example, the Opera experiment, right? The guys that said that neutrinos go faster than the speed of light, they are there. There's experiments there which just have huge tanks of liquid scintillator, meaning stuff that flashes when particles go in. They're just sitting there, you know, rolling their thumbs, waiting for a supernova to go off in our galaxy. If that did, they would detect enough neutrinos to actually do some physics with that. So they're waiting since 20 years for a supernova to go off. And there's other experiments in there. There's also then experiments to search for dark matter. The particular one that I'm involved with is not in one of the big shiny halls, but you go down a not quite so shiny tunnel. You see the huge air vent areas, and then you are in front of a tinfoil hut basically. And what you can see back there, this thing is actually the detector. We are talking about a cryostat that is. Here's a picture. We're talking about a price that is about that high and that diameter. Okay, and it's shielded even more, not just by the mile of rock, but it's even shielded even more to protect it from other parts of stuff. So, for example, we have on the outside water canisters, because water is great. It shields neutrons. Then you see here the gray stuff. Here you can see it there. That's like a total of 20 centimeters of lead. There's not just the 2 millimeters of lead that you have at the dentist, but we have 20 centimeters to get rid of all the radioactivity. And within the lead, there's this white stuff that's polyethylene, another 20 centimeters, again, to get rid of the neutrons. But then actually the polyethylene itself has also some impurities within it. If you buy it, there's also some radioactivity in the polyethylene. So you shield that by using another 5 centimeters of copper, right? And then, so what you can see here is a little bit like this shrine. That's where the detector goes. Now it's opened. So we can service it, we can work on it, and then eventually you close it, you put it all in, and it's sealed from all areas, shielded by this passive shield. So then this is what it looks like. This is the outside. You see there's the cables coming out for the signals and the high voltages. There's the cooling tower. I'll show you in a second how this works. It's basically a fridge, and cables, electronics, all that stuff that you need. Here's how our detector works. And you know what? I'm telling you a lot of detail. I'm not necessarily telling you this detail because I want you to take it home and be able to tell it to your grandma. That's not the purpose of this. What I want you to tell you is, what I want to give you on this particular example, I want to give you an idea of what the kind of technology is that we have to come up with to try to detect dark matter, and more importantly, to disentangle a possible signal from just random normal materials that we know. Here's our technology. So this is a picture of a drawing of this cryostat, of this detector. It's basically a bucket full of liquid xenon. Xenon, noble gas, noble element, right? You may know it. Some cars have this bright blue lights, bright white lights. That's actually xenon lamps. So we liquefy. That's to minus 100 degrees Celsius. How much is it in Fahrenheit? It's about 170 Kelvin. I have no clue. It's a cold slide. It's cold, like below. Yeah, something like that. So it's colder than at Antarctica, right? Anyway, but at that point it becomes liquid, and you have this bucket, and you fill it up. So also we put an electric field. We have cameras on the top and the bottom. Those cameras are actually very special. It's not really a camera. It's called a photomultiplier tube. It's a difficult word, but in physics it's really a workhorse. A lot of experiments use those devices. They can detect single photons. Fantastic devices, really excellent devices. And we don't just take one of them, we take an array. I'll show you a picture in a second on the bottom and on the top. So we have a total 200 pixel camera. Only 200 pixels? Yes, but it's 30 centimeters big on the bottom and 30 centimeters big on the top. It's all active, and it can detect single photons. So even if the dark matter interaction is very feeble, very faint, just gives a tiny speck of just any bit of light, we will see it. Okay, here's, I will show you here a true event that is building up. What happens if any particle hits, gets stuck or hits that liquid xenon, you get this little bit of a rubbing effect, right? So you get heat. Well, we are not detecting heat. We don't put thermometers on it. That would be difficult in liquid. Can't do that. But you get off a light signal, a flash of light, and you get off charges, right? Like the cat fur. Xenon is a nice property that you get both. The flash of light is an instantaneous flash of light. I see that right away. I see a flash of light in my signal, so time goes that way. Okay, and that's now we are ingenious physicists, so we give that first signal a great name. We call it S1. Isn't that fantastic? Maybe what happens then is, well, there's those electrons lurking around, right? Because any particle will cause that, a little bit of friction, will cause a little bit of charges. You have those electrons. If you put an electric field, you can drift them through the liquid. So for a while, they travel rather slowly, 2 millimeters per microsecond. You don't see anything. That's just the time that the electrons take to drift up there.
Are you just sitting there reading anything that happens to get through all of your barriers?
Yes.
Okay, I just
Yes.
want to make sure. Okay.
Yes, and I'll give you an idea about the sensitivity in just a second. Once the electrons are up there, we amplify them even more. Some of you may know, if you haven't heard of it, don't worry. If you have heard of a Geiger-Müller counter or Geiger counter, right? It's similar to a Geiger counter, what is happening out there. So we amplify that signal, and we get a second large signal, light signal. We get another flash of light in the gas. It's actually not a charge signal, it's a light signal, right? But it's directly proportional to the amount of charge. So it's the second signal that we see, so we call it S2, TFEA. Now that's actually, there's something very clever that we can do with that. It means for every particle interaction, we have 2 pieces of information. We actually even have more. One piece of information is how much energy got deposited in light. How much charge did we get out here? And the ratio of the 2 I can actually use to say whether there was an electron that happened that got stuck, or whether it was a neutron, or whether it was a dark matter particle. A dark matter particle would give less charge than common backgrounds. They give more charge. So looking at the ratio, and I'll show it to you in a second, the data, you can get more. But then there's another thing, that this camera is rather close, it's just a few millimeters. So because a flash of light is very localized here, you see those photomultipliers, those pixels, they will get all the light. This guy here sees nothing. So actually, if I look at the pattern where I see the light up here, I can tell the radial position where this event has happened. From the time it took here for those electrons to travel this distance, I know the C position. So what we can do with this detector is we know the position of every event in 3 dimensions. Why is that so great? Well, somebody mentioned it, right? Can you know what
time it happened? Mass.
Mass, time. The great idea came just from the side. It was all the particles coming through that stuff, all the known radioactivity comes from the outside. Okay? So all the known radioactivity will get stuck at the outside. It's being shielded, right? It's a dentist's lead skirt. So dark matter, on the other hand, we know that goes through stuff much easily. So I would expect dark matter to happen homogeneously all over the detector, in particular in the center also, whereas radioactive backgrounds I would expect to get stuck on the surface. I'll show you the plot in a second. What this allows us, because we can reconstruct the position, I can restrict myself and I can say I look for dark matter only in the central volume, not on the side, because that's where radioactive backgrounds are. Right? So that's one of the tricks that we play, one of the many tricks that we play to find that. Here's maybe a picture. So this is a picture of the bottom photomultiplier tube array. It's about that big, 30 centimeters in diameter. Same thing on the top. Here's a technical drawing. The bottom array, the top array. All this is wrapped by Teflon. By the way, Teflon is white, not black. Is shielded by Teflon. You see those small copper wires here that make a very uniform electric field. And what we can do with that is actually quite fantastic. If there's a single, the sensitivity of this device is fantastic. If there's a single electron by an interaction that is rubbed loose and that is, left at the bottom of this detector, the single electron will drift all the way to the top and generate a signal, a single electron. Also, if there's a single photon, we have a chance of seeing that. So an extremely sensitive device. The whole experiment is 161 kilograms. Within the active volume, we have some 50 or so kilograms, 60 kilograms. So that's, I mean, as heavy as, well, not even as I am. So, but like the mass of a human body. Now, if you look at the radioactive background in a human body, you or me, which is about the same mass, you will have thousands of radioactive interactions every second. Nothing to worry about. Natural radioactivity just happens, right? If you eat a banana, you eat potassium-40, you eat radioactivity. Fine, that's okay, that's totally normal, but bananas are healthy, right? This detector, because it's shielded so well, because it's made from only selected material, every screw that goes in this detector, we have beforehand screened and looked how big is the radioactivity in that, to select only materials that have little intrinsic radioactivity and not use human beings or bananas. Because of that, and because of all the shielding, the radioactivity is actually only at the level of 1 hertz, okay, rather than thousands of hertz. Now, this detector, the sensitivity of this detector is such that you have one particle interacting about every second, and we are searching for dark matter 24/7 for more than, so the data that I'll show you in a second, the data that I show you in a second is from more than 100 life days, so it was taken over something like half a year. 24/7, just like that. Okay. The sensitivity is such that if there's only 1 or 2 or 3 interactions from dark matter, we would have been able to detect that and to make a claim that we have found dark matter. So that's the sensitivity of those experiments that are at. Is there a question? Yes?
What type of materials do you typically use to produce that?
Right. So the liquid xenon itself is highly purified. We purify that on the site underground to prevent it from being contaminated again on the way. This is Teflon, which you get from a Swiss supplier. If you buy the Teflon from somebody around here, we haven't found a supplier who has such good Teflon. This is stainless steel. The stainless steel comes from a supplier in northern New York, again, because that's very clean. The guys they're the Swiss guys are worse. The photomultiplier tubes, they are from Hamamatsu, and we have actually had a campaign over many years where we worked with a company that makes those photomultiplier tubes to reduce the radioactivity of all the materials. So they send us the materials that they wanted to use, and like the different materials, and we told them use this, not this, use this, not this, thereby reducing the radioactivity. So, and in the cryostat itself, yeah, stainless steel also.
Did you guys assemble all this yourself?
Yes.
Okay. Are there predictions of what the probability is?
Yes, and the prediction is such that if yes, so there's a few predictions that have been made. The most naive prediction that was made was such that we should have seen it 20 years ago, but we didn't. Then people went and said, okay, wait a moment. If there's a Higgs particle, it was funny because we talked about it. If there's, I'll go in a little bit detail to answer this question. If there's a Higgs particle, which is what gives mass to everything, right? And now we have kind of discovered it. What that means is that we and this detector interacts with Higgs particles, right? If you put it on a balance, there's mass there. But it also means dark matter is massive. It has to interact via the Higgs mechanism, right, with the Higgs particle. So what this opens up is a bridge from us to dark matter. Via the Higgs particle, we can interact via dark matter. Okay, it's fantastic. I was very happy when the guys at CERN said that they have this indication that they may have seen the Higgs, because it's great. It's this guaranteed channel. I mean, it's hard to find something that I mean, it's hard to cook something up which would blow this bridge up. This bridge is really there, right, via the Higgs mechanism. And if this, and then you can now go and say, okay, how likely is it that with a detector like this, you find that? The predictions are such that we could have found it last year. We may find it this year. We're actually just in the final steps of analyzing the data, and we'll release it in a couple of weeks. You'll probably read it in whatever the result is. I don't know myself yet. We do a blind analysis. But you will know. The chances are, if there's those particles that I talked about, if they interact via the Higgs mechanisms, the chances are, let me try to get that from the plot that I have in my mind, something like 20 or 30% that we will find it within a couple of weeks, 20% maybe. We are right now, and I have a slide at the very end, building a bigger detector, 10 times bigger than that. And the chances that if this Higgs idea is correct, we will find it with a bigger detector, which we will build We started constructing this one already. The chances that we find it with that are, if those ideas are correct, 80–90%. If those ideas are correct.
In a 2-week period?
No, you would need to search with this bigger detector for 2 years. So we will, the chances are that we find it by 2017. It's not so long, right? We have 2012 already, so it's within 5 years, with about 89–90%, if those ideas are correct. Yes, ma'am?
So would it make a difference if you had a lot of those detectors?
Yes, yes, totally. If you have 2 of them, you only need to search for the dark matter half of the time. Right?
Okay.
Totally. Gentleman in the back.
Yeah, how much does something like this cost, and who pays for it?
Ah, okay. So this particular detector, okay, now what do we relate cost to, right? But if you relate it to anything that the public generally spends money on, highways, aircraft carriers, you name it, schools even, also that, but those things are drop dead cheap. This whole detector is, a few $1 million.
That's all.
That's all. It's not expensive at all. Now, who pays for it? The Xenon, all the various experiments I showed you earlier, they supported by different funding agencies. Xenon 100, we are in a very lucky position. We enjoy support from the National Science Foundation. We also enjoy support from the Department of Energy. We're very grateful for that. And our partners in Europe and overseas, they are being supported by their respective funding agencies: Switzerland, Germany, France, Portugal, Israel, so those funding agencies as well. However, this particular detector that we are talking, it shouldn't surprise you, is really, more than half of the cost is carried by the United States, by the National Science Foundation.
Is there any political friction or problems with this, like it's not worth it, or it's too much money, or going to cut your budget?
So the budget of the National Science Foundation is decreasing. It's not getting bigger, which is, in my mind, the exactly opposite thing of what you should do in an economical situation like this. But okay. So it is generally getting a bit more difficult to find research money. Having said that, it is being widely recognized, widely recognized by the community that those experiments are well worth the money. They are comparatively really cheap, and the result that you have is, within 5 years we may, or within 2 weeks, right? I don't know, but within 5 years we really have a good chance of discovering dark matter, which is at this stage one of the most pressing problems of physics all over the place, right? Because we know it's there. Try to convince you of that. So we want to find it. What is it, right? What the heck? So generally, I would say we are in a mildly optimistic scenario. I could tell you more after next week when we have a major review from NSF, actually. That gentleman was first up.
What is the window, the frequency window
Can't hear you.
for the photodetector?
Okay, so the question is, what is the frequency window for the photodetector?
Yes.
Let me see whether I get your question right. The xenon, I'll just say something and you tell me whether it answers your question. The xenon, when it gives off flashes of light, the flashes they are in the ultraviolet light.
Oh.
So you cannot see that with the naked eye. But again, we worked with the company that makes those very well together, and they push the sensitivity of those detectors into the ultraviolet regime so that actually those detectors can pick the light up. So it's frequency range, it's ultraviolet light.
So you are assuming that
that's a property of the xenon, not of the dark matter. The property of the xenon is that whenever it's being hit by a particle, it gives off ultraviolet light. Doesn't matter which particle hits it, as long as any particle hits it. And the reason for that is because what really happens on a microscopic level, and I have a slide about that. Just need to go back. I thought I would skip it, but now that you're interested, that's great. There's, how do you see particles when they get stuck in your detector? What can either happen is that if a particle just goes through your detector, you don't see it. Right? It has to interact with your detector. There's two things that it can interact with. It can interact with the electrons, or it can interact with the nucleus. What it interacts with depends on depends mainly on the mass of the particle. That's like if you are on a bicycle and you ride your bicycle and you crash into a truck, the truck doesn't notice. Right? If you crash into a pedestrian, the pedestrian notices. Okay? So if you have a light particle that comes, you see that only if it crashes into something light. If you have a heavy particle, you see that only if it crashes into something heavy. Right? Just think of traffic accidents. Now, radioactive backgrounds, alpha backgrounds are very easy to shield. We don't have to worry about them, just a piece of paper. Radioactive backgrounds are electrons or gammas, beta or gamma rays. So they are light particles, they will scatter off the electrons. Whereas dark matter, we said the idea that we have for dark matter is that it's a heavy particle, as heavy as hundreds of protons. We will see that if it interacts with the nucleus of the atom, because that's also 130 protons heavy. Right? So that's how we see it. So you can, what you see is then you have the electron or the nucleon that flies through your detector, and that is what generates the scintillation, ionization, and phonon signal. Right? That has nothing to do anymore with the dashed line here. That flies and leaves your detector. What you're looking at is you're looking at the nucleus which got kicked, and you see that flying. The great thing about that is, now that I'm at it, if you have two signals that you're measuring, you can measure an energy and another signal, you can distinguish between the two interactions. That's another way of dramatically reducing your background, because natural radioactivity is those kinds of interactions, whereas dark matter is this kind of interactions. Which is why, for example, the xenon detector that I just explained to you measures ionization and scintillation, and the ratio of the two tells you whether it was this or that. And I can show you the data in a second.
Why xenon? Why no helium?
Okay, why xenon? The easy answer is because xenon is very heavy nucleus. So basically, what you do is if we are in the picture of a fishing net, I have a fishing net, and as we fly through the galaxy, I try to catch dark matter. If your nucleus is bigger, more heavy, you have a higher chance of catching dark matter with it, right? So that's the easy answer. Right, you have more cross section. That's the technical term I'm trying to avoid. Yes, exactly. Yes, there was a question.
What's the relationship between dark matter and the cosmological constant?
Slim to none. Basically none. Yeah. Cosmological constant is one idea that we have what dark energy could be, and dark energy and dark matter just share the dark, not much else. It's also that dark energy is on a much weaker footing than dark matter. Dark matter is more than a dozen independent observations which all point into the same direction. Dark energy is 3 or so observations. Yes?
If the CERN finds the Higgs particle, are you just going to change the mathematics, or are you actually going to...
We're not changing anything because it totally confirms the direction in which we are going already anyway. If CERN finds the Higgs, or it kind of did find it, that's, when I read that, I was really happy because it meant, yeah, great, you could really be, we could really be on the right track. So I'm not changing anything. It's what I expected all time, all along.
I understand that. What I am trying to get to is that if the Higgs particle sorry about it. Let me think about it for a second. I had a thought and took too long.
Sure. Yes, there's another question.
Yeah, following up on the previous question, does possibly related to that, does dark matter have anything to do that you would know of with the accelerating expansion of the universe?
Well, okay, so the answer is the same answer. It's not really. The accelerating expansion of the universe is related to what we call dark energy, and you have much less an idea about dark energy than what we have about dark matter. I think I tried to give you an idea about it today that, we don't really know what dark matter is, but, we have a fair idea. We know what it isn't, we know where it is, we know how we can search for it. For dark energy, it's much less than that. We don't know where it is, we have no good idea of what it could be. We have not the faintest clue of whether there's any way to really detect it, and we just have no idea about that. Yes, please.
Very naive question, but if your xenon...
Naive questions are great, those are the ones that I can't usually answer. That's fantastic.
If your xenon nuclei are large,
yes,
and dark matter cores are large and extremely prevalent, how do we explain the lack of interaction? Do we have an explanation for the lack of interaction?
Yes. So in this picture, okay, so something that interacts a lot, for example, is photons, right? Light. I mean, I can't look through my hand, right? So, and the reason for that is because if you have a light particle that comes along and meets an electron, well, it doesn't talk to the electron directly. It needs to have some mailman that says, "Hey, electron, I'm here." And then the electron can come back and say, "Yeah, I'm here too. Let's meet and have some fun together." That's what we call an interaction. So what you need is you need to have some what we call exchange particle, and what it really means is just mail, right? I mean, you need some letters that you can send back and forth between particles. If you have letters being sent back and forth, then you have a messenger particle being sent back and forth, then you have an interaction. So you need particles that give interactions. And it depends on which particles it depends which mail you can read. Can you only read mail? Or can you also receive parcels? Or maybe you are only up for email and you don't do anything else, right? Then if somebody tries to send you a parcel, you'll never receive it. And that's exactly the difference between various particles. They interact via different channels. Different channels are the different forces that we have. There are 4 forces that we know of. There is the electromagnetic force, and what's the mail that is carrying the electromagnetic force? The particle, the messenger particle? No. Electron? No. Not the electron, it's a photon, actually. Photon is the carrier of the electromagnetic force. So if you have say that cat fur, and you have this hand standing, what there's constantly happening, there's virtual photons being exchanged. There is the weak force. The weak force is exchanged via W and C bosons. There's actually 3 particles that do that. So there's there's different sizes of parcels. Right? Then there is the strong force, and the carriers of the strong force are, somebody knew it? Gluons, right? And finally, there's the gravitational force. We haven't all those carriers I talked about so far, all those mails, emails, parcels. We know the gravitational force is exchanged via what we think are gravitons. We haven't caught gravitons yet because gravitational force is so weak; they are hard to catch. We try to catch them in gravitational wave detectors. We'll see whether we manage. And now the question comes for the dark matter: what kind of those messenger particles can dark matter read? Can dark matter receive parcels, or just mail, or maybe just email? And we think that dark matter cannot, for example, receive electromagnetic interaction, photons. Because if it did, well, we would have seen it, right? I mean, if it would interact with light, we would have seen it. We didn't see it, okay? We also think it cannot interact via the strong force, because the strong force has actually a weird property that it tries to clump stuff so strongly together to a nucleus, even despite the electromagnetic force tries to pull blow protons apart. So we also think it can't do that. We know it can receive gravitational interactions. We know it can receive gravitons. And we think, if those ideas are correct, that maybe it can also receive this mail, which is exchanged via those W and C bosons, this weak interaction, which is why we call them weakly interacting. They do interact via the weak force. That's what this term means. I talked a long time. I forgot whether I answered your question.
That makes perfect sense to me.
Right. So that's in a sense that's a little bit related to that, right? I mean, which possibilities do you have? Yes, and then there's a 5th mail, which now we just recently are about to unravel and are able to read ourselves, which is great, right? If you can tap into one of those mail channels and read it, and that's the Higgs channel. That's the Higgs boson, which mediates mass. And because it mediates mass, and if this exists, it's very natural to believe that dark matter would also be able to receive and send Higgs mail. So it's great that we can now start to read Higgs mail, because we can see whether we can find dark matter via that channel.
Thank you very much.
Sure. Yep.
Excuse me. There is any alternatives to explain the gravitational stability?
Okay. Yes, so the question is there any alternative to dark matter?
Yes.
Totally. Let's go back to this slide. You remember this one here? Okay. Well, what we observe, again going back to the Milky Way, we observe that the stuff is going very fast, and that the mass that we observe creates less gravity than we would need, right? So we would fall off the merry-go-round, right? That's where we are. The galaxy is spinning too fast. And one way of explaining that is to say, oh, you need additional mass, which creates additional gravity, which keeps all everything together. The alternative idea is that you made a mistake in your calculation. Okay? That sounds a bit funny, but it's actually not, because you could say, well, how well do we know the gravitational law at such large distances? Right? Couldn't it just be that something happens to the gravity, to the law of gravity? And really, what you can explain you can modify your law of gravity to explain the galaxy clusters as well, to explain the rotation curves as well. But what you can't explain is that you have an offset here if you just modify the gravitational law, because still you should be centered around those blobs, but you are not. So a modification to the gravitational law does not seem to work, at least not in this one example.
I'm sure it's not, but I'll ask it anyway, is the quantum level of things, is that significant at all, where particles are instantly winking in and out of existence and maybe imparting some sort of gravitational force on each other and instantly disappearing? Anything like that significant at all?
Okay. Anything quantum in there, right? Quantum sounds so cool, it has to be in there. Okay. Now you asked about it. Now you get the answer. Yes, there is. Quantum is important. Okay. We have the radio astronomy expert here. If you you have ever seen a radio telescope, they have those. Actually, they are made from meshes, yet they can reflect radio wavelengths. Or if you look, a better example, if you look at the antenna for radio, they're actually very far apart, yet they can interact with the radio waves. Okay, so the wavelength the wavelength tells you how big a size you can probe. The radio telescope that is actually made very uneven and just out of a mesh to a radio wavelength looks like a perfect reflecting mirror, because the imperfections are too small for the radio wavelength to be able to see it. Does that make sense? I lost you, I think. Hey, come on! I mean, if you are nodding now, you didn't get what I was saying, because I didn't understand myself. Let me try from another point of view. Quantum mechanics. Okay, we wanted to have that word in there. So quantum mechanics tells us actually there is something like a particle-wave duality. Okay. Wow! Now you didn't expect me to talk about that, right? Okay. Here's one big misconception. You know what? I stopped talking about my talk here. Thank you very much. Now here's a big misconception about quantum mechanics. Okay, people say, what are particles? Are particles waves or wave particles? I mean, they say they can be, they can be both. And how do they decide what they are? Misconception. An electron is not both a particle and a wave, or sometimes a particle or a wave, depending which experiment we do with it. Did you ever have a talk here about particle-wave duality? No? Oh, you should have one. It's actually quite interesting. Misconception is an electron is neither. It's neither a particle nor it's a wave. It's a quantum mechanical entity, and the only way we can think of it is by thinking of it, depending which experiment we do, thinking of it as a particle or a wave. But the electron doesn't care about us, right? The electron is a quantum mechanical entity. Okay. So having said that, those dark matter particles, like all particles, and like you and me even, can also be thought of as waves. And you can calculate the wavelength, because that only depends on the mass and the speed. Okay, so I can calculate the wavelength, and I find that the wavelength of those particles. You wanted to have quantum, okay? Don't complain. The wavelength of those particles is actually larger than the size of a nucleus. And what that means is that the dark matter particle, when it comes, it cannot look into the nucleus. It only sees there's something there, but it does not see the structure of the protons and the neutrons. Okay. This has important consequences, because it means if you make your nucleus larger, you get what is called a coherent interaction. You actually square your interaction probability. So that's another reason somebody asked why we use xenon. The quick answer was to say, because if it's big, you make a fishing net which is tighter. The better answer is, because of quantum mechanics, you make your probability, you square it. You make it even better than just by the size. You make it better by the size squared. So that's a quantum mechanical effect. In case you wondered whether there's any quantum mechanics in there. Yeah, but there is. Look, I talked for almost another hour. Guys, I want to thank you very. I just stop here right out of the random, and I'll go not go as long as there are questions. I promise that. Sorry for being late again. I want you to thank you very, very much. I think you have been an excellent audience. I much appreciate it.
Thank you very much, Dr. Lang. I hope we have you back sometime again.
Oh, anytime.
He mentioned another topic, so having back on. He thinks we should have a talk on it, so he's back Dr. Lang back.